Hello.
Hello.
Good afternoon.
Good afternoon.
Hello, Mr. Khaled.
Yes.
Teacher,
Yes,
can we take?
yeah, I can hear you.
Okay. I have a suggestion, sir.
You have what? Suggestion?
Yes. Can we take another break? Because 3 hours continuous is very long, sir.
Okay.
I agree.
We can discuss that.
Once
So,
everyone joins.
Let's discuss
sure.
it now in the beginning.
No, but once
at which time would you like to have?
After ناخذه بعد ساعة و50 دقيقة من البريك.
so like in the middle point. So
Yes.
an hour and a half after the first break.
Okay.
So that's
okay.
Yeah.
This is first is until 5:55. Then something like
7:30.
half past okay 6 7:30, something like that.
Yes.
10 minutes. 10 minutes is enough.
Okay. All right. Something like that.
Okay, thank you.
All right. Okay, everyone here? Not yet, not quite, not everyone yet. We'll continue today with kinematics, and now the next topic is optimal trajectories. So if you launch at certain point, from a certain point a missile, then what is the region where you can hit the target? So let us say that you launch from the origin, coordinates are 0. So here is x, here is y. Okay, you launch from this point here at a certain angle alpha, and then you ask what is the region where you can hit the target. Now, do you remember how to derive this shape of this region where you can hit?
For me, yes, sir.
Sorry?
I remember what it is, but not how to derive it.
Okay. Now you can try thinking. So first, here is a problem. Find the region. Function of y is smaller than function of x. So that you can hit the target inside. So now your task is to find this function f of x. Okay, this is your task. And now, before you proceed, you try to formulate plan your how you will be going to solve it. Like, don't start immediately, but try to figure out what would be a viable plan, work plan to derive this thing here. Okay.
What's the question again? Sorry.
Okay. You have you can launch missiles from this point, x equals 0, y equals 0, with initial speed v0, but you can choose angle alpha. And now,
should we use calculus?
Yeah, and now you need to find this region where you can hit the target. So let us say you have a function f of x, and the region is defined as y is less than f of x, and then you can hit the target. And if it is larger than f of x, then you cannot hit. Now the question is, what is f of x? Okay.
I have an idea.
Yes.
Should I try it? Should I try? Are we going to try this on our own? Or?
Tell us what is your idea?
Okay. What I think you can do is have a function that depends on the angle alpha to find the maximum height in at a certain y position. So, for example, at a certain x position. Sorry. So, for example, let's just say that at x naught, so like at x naught from the center of the parabola, you define a function for the height that depends on the angle alpha.
Okay.
And then you
I got it.
find the maximum.
But now let me ask you, was this your first idea what you got, or you tried to
First idea.
First idea. Okay. Now please try to analyze. Is this a good idea? Is it easier to perform such kind of calculations?
If you are a math freak, yes.
But are you a math freak?
No.
Okay, so then it might not be the best approach for you.
Definitely, yes.
So any other suggestions? Okay, in such situations, don't start doing immediately according to your first idea. Because your first idea, unless you just immediately see through the problem, quite often first idea is not necessarily the best idea. So take a little bit time, like 5 minutes or so, to think if maybe there is a better approach. Okay. Now, any other suggestions what we can do?
Yes, I have.
Okay, I'm listening.
We have to get rid out of the angle.
Sorry?
We have to arrive to an equation that gets rid out of the angle. Because this function does not depend on the angle.
Yeah, this does this does not depend on angle, but for each target, what you can hit on this shape, there is a certain angle under which you can under which you need to launch.
Yes, all the angles will be real, so only real values.
Okay, I'm afraid I didn't quite understand. I didn't quite understand how we are going to calculate.
I have a suggestion.
Okay, please.
You can take a particular throwing angle,
Yes.
and then find when like this is valid. Like, what is the limit of that to be valid? So like when that trajectory of that certain angle like can't reach, like the region where it can't.
So you can calculate, but this is if you take a certain angle alpha, then what you have is something like that, maybe. Okay. Now, what will you be doing with that trajectory here now? Okay, so go to fix alpha, and then here is your trajectory. You can reach this point here on this shape. Now, what next?
Could we use some geometry, because we know that the region itself is a parabola?
How do you know?
Observation.
Observation. Now, yeah, it is parabola, but actually it is not because of observation, but because of calculations, and this is exactly what you ask now to do, to derive this, that this is parabola.
I mean, like, we find the trajectory of one certain angle and find what like when the solution of that certain angle vanish, and like that will be the limit of the trajectory.
Okay, we fixed alpha, and then trajectory is going something like that. Okay, now what shall we do with this limit? Okay, at the limit it goes down there.
At some point, this is going to touch the. This is going to touch fx at some point, which is going to be, I guess, the maximum, you could say.
Okay, possibly. You need to perhaps motivate it in more details, but yeah, probably it is going to touch. Okay, then what shall we do now? How can we derive this point where it is touching?
Mr. Khalid,
Yes.
I tried to apply Hassan first method, and it is not that long.
What did you do?
I tried to apply Hassan first method to find the maximum height at a certain x value, and it is not that long.
And you solved it.
Yes.
And what is the answer?
Y equal to v naught square over 2g minus g over 2 v naught square times x square.
Okay. Now, what you need to do is to find this shape. Please tell me what this shape is. Then.
It's parabola.
Yeah, but formula. Parabola, yes, but formula.
Yes, I told you the formula.
Ah.
It will be y is less than v naught square over 2g minus g over 2v.
Once again, please tell me. Okay, f of x equals
v naught square over 2g.
V naught square over 2g
minus g.
Minus
g over 2v naught square.
g over 2v naught square
times x square.
X square, yeah.
Hassan method.
Okay, you did it using Hassan method. Okay.
Yes.
You maximized, you maximized and then did calculation.
Yes.
Okay. But I still well, my suggestion was a little bit different because it was not quite clear how well you can find the maximum. So my suggestion was to work in such a way that suppose we formulate the question in a little bit different way. Suppose we have somewhere point which we want to hit, okay?
Okay.
Either here or inside or outside. A pair of coordinates x and y. And then we ask under which angle should we throw our missile so that it would go through this x and y. Is this easy task or not to derive an angle by which you need to throw in order to reach this point?
Easy.
Yeah, it's quite easy. But now, if we do it correctly, then apparently there should be no solution when it is outside. It's obvious, right? If it is outside the region, there is no valid angle under which we throw. So basically, what we are expecting if we do that way is that we find angle under which we need to shoot in order to hit target at xy. Then if xy is inside, then there are solutions. If it's outside, then there are not. So no solutions. So basically, you would expect something like perhaps a quadratic function or some quadratic equation, or something else, which sometimes has solution and sometimes hasn't. And then just the shape, the boundary between this and that is the limit case when the solution disappears. So if you have quadratic equation, it means just discriminant becomes equal to 0. If discriminant is negative, there are no solution. If its discriminant is positive, there are solutions. So to me, at least, it sounds much easier to do than maximizing and things like that. There is one step less. You need to maximize, but here you don't need to maximize. Here you just need to write equation by throwing angle alpha and have a look when the solution disappears. All right.
All right.
Actually, I think most of us have seen this derivation.
Sorry?
I think most of us have seen this derivation.
Most of you have seen this derivation.
Not sure.
So what you're saying is that you don't want to exercise. Is that right? Is that it?
No. That's it.
Okay.
I mean that as long as we know it, let's do it together. Like, or if someone wants to drive it himself, it's up to him.
So, Muhanna, do you want me to show solve this, or would you like to try yourself?
I knew the derivation.
You know the derivation. Now, let us do it that if you know the solution, then you should be able to do it very fast. Okay. So please, those of you who have solved it before, I expect you to be able to do it very fast. So please start and do it within 5 minutes. Okay. We are not going to lose much time then.
Okay, no problem.
Okay.
I finished the ride with that method.
And you got the answer?
Yes.
Very
Same
good.
for me.
And now I'm going to do it very fast here as well.
I have a question.
Yes.
What is D?
Discriminant of quadratic equation.
Okay. So you're looking at the discriminant and saying that if the discriminant is
No,
not,
screw zeros and the solution disappears.
if it's less than 0, okay, yeah.
Okay. Hang on. So, everyone finished with that?
I have a question.
Yes.
So the quadratic equation you have right now is for tan alpha, right?
Yeah. Theta. I did.
Okay.
You know the tangent as theta.
Okay. And then you found the discriminant, and then you just said that when the discriminant is equal to 0, then it's between.
There is no throwing angle. You cannot find a throwing angle, and so if it goes to negative. If it's 0, then there is only one solution. So we can see that for any if discriminant is positive, then there are two solutions. If discriminant is 0, which means that we are at the envelope of as the boundaries region, there is only one angle, and outside there is no.
I feel like the solution, once you know the idea, it's not very, very difficult. But I think that for me, if I had to like make the idea up, I would not be able to, because I don't think I could like create this solution. I could follow it along, like if I know the idea, but I can't find the idea for a solution like this.
That is exactly why I said that it is always worth taking time out and think what is the best possible route. So one possibility, yes, is that we find maximum, like fix certain x and look for maximum, but this seems to me at least like a lot of work. But what are other possibilities? Okay, we can proceed this way. And then once we got this idea, it seems to me at least more feasible than the previous one. So I would going to try out if this work out, if I can do that. And then what it means? It means that I need to express trajectories here. What we have here is trajectory written through parametrically. Parametric curves are so that x is a function of t, y is a function of t. So this is called parametric curve, meaning that that t is here and here, and as long as you let t run, you can go through all the curve. So first we write it parametrically, parameter being t, but then we can eliminate t because no one asks about time, we're asking about angle. So if we look here, it becomes clear that we can eliminate easily t, and then we have an equation which relates x, y, and alpha. And this is exactly what we wanted. This is equation from where we can express find the throwing angle alpha. Now we have tangent and cosine square. Once we do that, but then if you have some experience with trigonometry, you just immediately recall that okay, cosine square can be expressed in terms of tangent, and tangent squared, and then because tangent is already here, if all the other trigonometric functions are also tangent, then this would be equation for tangent. So that's how you quite often the trigonometric functions are solved. So here it would be handy to have certain experience in solving trigonometric equations. Okay, so we write equation this way, but now we know that if we want to find alpha, then we need to bring all the trigonometric functions replaced with a single trigonometric function. So we have sinus alpha, cosine alpha, tangent alpha, but we can easily express whichever way you want. So in this case, cosine square in terms of tangent, and then is the equation for tangent. Sometimes if you have double angles and things like that, it might be more difficult, but here with just cosine and tangent, it's quite easy. And then we have equation in terms of tangent. So y is at left-hand side, right-hand side is this thing here. This is equation for finding alpha. We just rewrite it in terms of tangent, equation for tangent. And then the rest is already easy.
Teacher,
Yes?
in the graph, what does when you equal the discriminant to 0?
Yeah.
What does that in the graph mean? That
it means a trajectory at that x and y, which corresponds to d equal to 0. At that point, the trajectory is touching the envelope. So let me, I'll clean this now to make more space, and then I show you. We can keep this formula here because this is we are going to use. We throw from here, and here is envelope. Now, if you fix a certain point, you can have two trajectories, one of which two throwing angles, one which goes that way. Both of them are going to touch the point. Okay, one goes that way, the other goes that way. One is touching the envelope before this point, and the other is touching envelope after. But if you take point at the now, suppose you start moving this point which you want to hit. Like if it's a moving object in here, it starts moving, and then these two trajectories will start coming closer and closer and closer. And once you reach this boundary here, these two merge into one. These two solutions, you have two solutions, alpha 1 and alpha 2, now for throwing. As this point approaches, is approaching the envelope, then the two angles become closer and closer until they merge. All right?
Yes, it's a very nice solution, derivation for it.
Thank you.
I remember before, I was solving a problem with this parabola. With
Yes.
this, I mean, with the trajectory, like the maximum parabola. I
Yes.
forgot what it's called, but and then I forgot something, and I had to write, and not had, but I wrote a program, like in Java, and to find the maximum at every point.
Okay.
I don't know. It was. It is what happens when you are bored.
But it is good that you know Java. It is also a useful skill. Right now, I am teaching also master students. I have lectures with master students, and I give them sometimes tasks where they need to make simulations. And now I am also having trouble that they cannot make code. So knowing Java in itself is also good, but of course knowing how to calculate some things is also
Yes. Simulations can't do everything, because the bad thing about simulations is if you're bad at math, it's not going to be very optimized.
Yeah.
Which is horrible.
Yeah. Yeah.
But it can help you prove a lot of theorems very easily.
Yeah. Yeah. All right. Now we have this curve here. The next thing is to find the focus of this ellipse. Where is this focus situated? Now, in order to first question is what is focus of ellipse? So we have ellipse of parabola. Now we have different so-called conic sections. So what is conic section? You have a conus cone, okay? Like you take a straight line which forms the angle alpha was vertical, and then you let this line rotate, and then it draws a surface which you say is a cone. But now you have two cones touching each other, right? And conic section is if you take a plane and then intersect it. Now here at the intersection you have some curve. And now you have different possibilities for conic sections. One is ellipse, the other is hyperbola, and then is parabola, and also you can have just straight lines. So
what do you mean by straight lines?
Okay, how you can obtain straight lines? Very easy. You obtain a pair of straight lines, for instance, if you take a just vertical cut like that, then you will be having the straight lines. Am I right? If your intersecting surface goes through this tip of these cones, your intersection lines will be straight lines.
Wouldn't it just be, if you do that, wouldn't it just be, two straight lines, not just one? Okay.
Two straight lines, yeah, a pair of straight lines, yeah. So you have different options, ellipse, parabola, hyperbola, straight lines, and then a special case of ellipse is a circle. Ellipse, for instance, you can also obtain ellipse when you take a cylinder and cut the cylinder. This will give you also ellipse. Okay? If you take cut like that, you have also here ellipse. So if you have some bottle or a cup with circular rim, and then you look from the side, you see a perfect ellipse actually. Because in that case you cut you project a straight or a circle on the angle to your looking to the perpendicular to your looking line, and then this is this ellipse. So but why we don't say that this is a cylindrical section, but you have a conic section? Because conic section, with cylinder you can obtain only ellipse, but with conus you can also obtain hyperbola. If your plane like goes something like that, intersection the plane with which you intersect, then here you have hyperbola was now. So and if you want to obtain a parabola, then you intersect so that your intersecting line plane is parallel to this line here. Okay, if your plane goes like that, then you obtain parabola. Now I don't think this figure is any longer very clear, but you got the idea. I hope that by intersecting cones you can get everything, all these things. So that's why you call these conic sections. And now there are, as far as ellipse and parabola and hyperbola concerned, there are nice geometrical properties of these figures, and namely, there they have a foci. So if you have ellipse, then it has two foci, and sum of distances equals to major semi-axis. So if double major semi-axis, if major semi-axis is A, then L1 plus L2 equals 2A. Now, on the other hand, if you take here a ray of light from here and let it reflect from the inner surface of this ellipse, then it is reflected to here, which means that these two angles are equal. Okay? Now, these two properties are actually interconnected to each other. In which way? Who can tell me?
What was the question?
Now the question is that if we take ellipse here, it has two foci, and we know that there are two properties for foci. Sum of distances of arbitrary point on the ellipse, sum of distances to the foci is a constant and equal to double major semi-axis. And the second property is that if you take a ray and let it depart from one focus, it is reflected to the other focus. Now, in which way are these two properties interrelated, related to each other? What physical principle relates these two things to each other?
Similar.
Sorry?
Mirror.
Once again?
Mirror.
Yeah, I
Geometric
don't think so.
rays.
He said if it's reflected on an ellipse, it will go to the other focal point.
Yeah, it will. My question is, what physical principle relates these two properties to each other? First, the sum is constant, the other is angles are equal. What physical property relates to these two? Which physical principle relates these two properties to each other?
Fermat.
Fermat, yes, exactly. Fermat principle. And can you explain why Fermat principle relates? How would you discuss that Fermat principle? This is, if you know one property, why the other is also valid?
I have horrible memory with names, so can you?
Okay. Fermat principle states that light goes along the shortest optical path. Light from one point to the other point goes along shortest optical path.
Maybe we can prove that the reflection with equal angles is going to give us the shortest path.
Well, okay. What actually Fermat principle does mean? There are, as a matter of fact, there are situations when seemingly Fermat principle is not valid. Let us consider such a situation. So here is source, and here is destination, and then here is a glass plate. Here is a glass plate. Glass plate. Let us make glass plate like that. Now, glass plate makes optical path longer, right? Now, a straight path is like that, but it goes through the plate. This path here is optically short, actually. Okay, the red path is optically shorter from A to B. Now, but how will light go from A to B? Will it go along the black line or will it go along the red line?
The black one.
Black line, yeah. So here is a situation where Fermat principle is not valid. Well, it is valid, but we need to formulate it correctly. So why here your light will not go along the shortest optical path? Well, it is because Fermat principle, what it actually means is that the path is the shortest among all the neighboring paths. So if we take black path here and take another path which is infinitely close to this one, it will be longer. So in this sense, this line, the straight line here provides local minimum for the path length. If we take another path which is very close, it is optically longer. That's, this is Fermat principle, that path goes along such a line that if we take infinitely close line next to it, then it will be optically longer. Now, what if we take here this red path here? So if we take red path here, then if you go here, start moving up, yes, if the optical path will become longer because just the path length becomes longer. Okay, now if you go this way, optical path becomes longer because it now needs to go through the blade. But the thing is actually there is discontinuity, that just if you take this infinitely close to the blade, then the beam will optical path length will have a jump. So well, if we take like a distance to which let's here be x, the distance where the path intersects this point here, then our path length would be something like that. So here is optical path length. Here vertical is optical path length, and here is the coordinate x. Okay. Now we take, if a path goes straight here, it has local minimum like that. Goes up, and then it goes down, and then continues going up. Now the thing is that here, if we take here in the neighborhood, these are all neighboring paths here are slightly longer, but still close. Length is very close still. But here, if we take a neighboring path, it is already starts going linearly up. It's not like, see, here is a piece of parabola, but here it starts linearly growing up. And this is not where the Fermat principle works. So here, the Fermat principle does not work. Why it is like that? Actually, you can say that Fermat principle derives from the Huygens principle. Huygens principle is that in order to find how the light goes, what you need to do is you need to build wavefronts. Let us say that here at point A is a wave source, and then wave source starts at first moment of time, light travels and forms a small circle around it. And now at next step, you can put here light sources at the surface. Each of them creates a new wave, and then envelope of these is a new wavefront. And then you put here waves, and here another new wavefront. So basically, the light here is a sum of all the waves which go through all the different along all the different paths. Okay, it starts here. Here creates another wave. Here creates. It's like a sum of all the waves. But then you need to sum up. Like if you think about wave optics, you need to sum up all the waves. And some waves add up constructively, and some of them add up destructively. And it appears that those which dominate in the sum are just the things here near the maximum and near the minimum. Well, I don't know. Now it was quite a long, long explanation what I gave you, but well, it's somewhat similar. You know, a rainbow. Do you know how a rainbow is formed?
Yes.
Mm-hmm.
So light is usually white light is formed with all colors, and then each one of these colors has different wavelength, and I forgot what it's called, but when light passes from using Snell's law, when light passes from two places with different speeds of light, like inside of glass, for example, then this white light itself is going to spread out, kind of, because every single light wave, which is like red light, blue light, and so on, each one of them has a different frequency, and so that's why they
but
reflect at different angles.
The main question is why there is a certain angle under which you see bright light. So if you look at the rainbow, there is a like arc, the direction where it is bright, and the other side it is not as bright. So why is that? And the explanation is as follows. So if you have a droplet, let me
What
make.
did you say? So?
Yes.
What did you say?
What? Sorry.
What did you say?
I'm going to explain why you have a rainbow, why you see a rainbow. That rainbow is formed on the droplets. And now suppose here is a light direction of light coming, and you have different beams. One beam goes like arrives here, another beam arrives here, and so on, okay? And some of them bypass just. Now let us study how they are deflected. So here is the center, and now this is deflected towards the center. Okay, let us take this one. So here is radius vector. Now this is deflected somehow, and then it goes here like that. Okay, here is how the light is deflected. Now you can describe this by impact parameter B. This is distance between this beam here and the symmetry line, and the deflection angle alpha. Okay, and then it appears that the deflection angle alpha has now extremum at certain value of B. So if we plot here alpha as a function of B, alpha as a function of B. Now when light goes, sorry, here actually here there is no extremum, but rainbow is actually it appears after one single partial reflection from the inner surface. So there is a full internal, total internal reflection, but there is partial internal reflection. So at the interface, yes?
How is that related to kinematics?
This is related to Fermat principle. I am going to explain you why Fermat principle works and in which cases it works.
I mean the rainbow.
Yes. Using rainbow, I am going to explain why Fermat principle works.
Okay.
So we have beam which is refracted, then reflected, and then goes out. And now we have here angle alpha by which it is deflected. And now we have if B is 0, it just goes back. So alpha is 0 then. And then it goes up, and then it has certain extremum. Here is how alpha depends on B. Okay, and now let us have how much light arrives at certain angle alpha. We look into the ear, and there are droplets everywhere, and light falls on different values of B. But we look at a certain angle alpha with respect to sunlight. So sun is over there, and we look in that direction. And we look in that direction and see if we have light. Okay, if we look at at certain angle alpha, we are seeing those light beams which are come out from that direction. Now, which correspond to this deflection angle alpha. Now we take certain alpha, and actually we take a certain range of alphas. And then which range of B's correspond to that? If we take here, we have a relatively narrow range of B's. But if our alpha is close to maximum, then we have wide range of B's. Because the curve has maximum, narrow range in alpha corresponds to wide range in B. Is that clear?
Yes.
So if we look at that angle alpha, where the curve has maximum, we have a wide range of B. A wide range of B means more light coming, because light comes from with all the B's. And if we have wide range of B's, there are more light coming. So that's why you see bright rainbow in that direction, which corresponds to maximal deflection angle alpha in the droplet. Okay, now coming back to here in the Fermat principle. If we say that light at B is a sum of all the possible paths from which light can come, then we can say that they all we need to add them all, but there are more paths close to extremum, because if we depart slightly from the extremum, then the optical path difference is very small. And they are, because of that, they can nicely add up constructively, because they have all the same wavelengths. If the optical path length starts changing, then because opposite waves in opposite phase add up destructively, here they add up destructively, and that's why if you take like this, that if our beam goes like just next to the plate, or through the plate, we have this point here. So here it goes through the plate, it is long. Now through next to plate, it is small. But here it is, there is no local minimum here, because here it starts going straight up. Here you take next beam and it adds up destructively. Unlike here, if you take next beam, it has almost the same wavelengths. The reason is not that this beam is the shortest, but it means that the neighboring beam is almost as long as this one. That's why you have Fermat principles. If you take beam which goes along the shortest optical path, and the beam next one has almost exactly the same path length, which means that the next light beam adds up constructively and not destructively. That's why light will travel along such a path that paths which are very close to it have almost the same length. It means that it has local extremum, local minimum optical path length. And now if we come back to this ellipse, actually from where we came from the ellipse. And now if one path, if we say that L1 lengths are all equal, whichever point we take, optical path lengths are equal. It means that just Fermat principle is valid for any such path. This path has a local extremum, so length will not change as we move this point here along the curve. Which means that all the passes will be valid optical passes, because they all have the same length. So here the important thing was not that one pass is longer than the other, but the important point was that neighboring passes have the same length, or almost the same length. And here, whichever path you take, neighboring passes have almost the same length. And that's why, due to the property of L1 plus L2 equal constant, all the other paths satisfy the Fermat principle, means that all the passes are valid optical passes. But once they are valid optical passes, it means automatically that the angles are equal, because we know the reflection law that angles must be equal, right?
Right.
So it was quite a lengthy explanation now, but I thought it is important to do for you to see connections between different parts of physics. In physics, different parts are important. Like someone here told that why I am telling something with optics which is not kinematics. I was telling this exactly because you would be able to see connections between different parts of physics. Okay.
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 Yes.
All right. And now, there is a focus of ellipse. But there is also focus for hyperbola and focus for parabola. So parabola, you can just think as infinitely long ellipse. Infinitely long ellipse. Thing like that. So here is one focus, and the other focus is here at infinity. Okay, which means that if the other focus is at infinity, then the optical property would be that a beam which goes parallel to the axis will go through the focus. Okay. If you think about parabola as infinitely long ellipse, then it is easy to see that a beam which goes parallel must go to the ellipse, to the focus. And similarly, if we distance to the other focus, so L1 plus L2 is property. But because distance to other focus is infinite, you can just take arbitrary line here and say that L1 plus L2 is constant. L1 plus L2 is constant. Where this is arbitrary reference line from why we take measure the distance. Or this reference line actually can be taken to the other side. We can take this reference line to right hand side. And then we can find here such a line that this segment here equal to that segment. Okay, now for this point here, we know that L1 plus L2 is constant. But if this distance here is D, then, and let this be here, the red segment be L3. Then we have L1 plus L2 is constant, but L1 is D minus L3. D minus L3 plus L2 is constant. Okay, now constant. But D itself is constant, D is distance. So we see that L2 minus L3 is constant. And for this point here, it shows that L2 was equal to L3, which has to took this line such a distance that this segment is equal to that segment. Now, if in that case, for this particular point here, this constant is equal to 0, and it will be equal to always. So
please explain that. Why is it going to be 0?
Okay. Because I drew a red line. Not any arbitrary line which is parallel to this line here, but I drew it such a way that the distance of this point from the red line equals to this L2.
So it is from the vertex, double focal.
Well, the procedure was like that. I had arbitrary point on the ellipse, and then I measure the distance from the focus, and then draw a line which is parallel to the axis at distance L3, which is equal to L2.
Okay, so you assume that.
I take one out of many possible lines. I take such a vertical line for which this distance equal to that distance.
Okay, I understand.
Okay. And now, but this was valid only for one point. But because we know that this property is valid for arbitrary, L2 minus L3 must be constant. Okay, let us do it such a way. This is constant. And now, because I chose a line so that L2 minus L3 is 0 for this particular point, but because it is constant, it remains constant, being equal to all the other points as well. So that L2 minus L2 equals L3 for any point on the ellipse. Now the distance from that red line, we have equal distances. Okay, this distance equal to that distance here. And then this red line is called a directrix. The directrix of this parabola here. All right.
All right, clear.
A directrix is such a line that the distance from any point of the ellipse of the parabola equals to the distance from the line. So focus together with directrix define your perfectly ellipse. So you can tell parabola. So in order to define ellipse, you can just give one focus, the other focus, and one point on the ellipse. So basically, you need to give semi-axis. But for parabola, it's just enough to give focus and directrix, and this defines your the shape of your parabola.
Okay, teacher, how can you find the coordinates of the force?
Coordinates of what?
Of the focus point.
Okay, this is what I'm going to do. This will be a task. But
I mean, in general, not only for. Okay.
Yeah, we are going to do it in general. Yeah, don't worry. This is exactly what I'm going to do. Now, but before we go to that, let us finish with the foci of hyperbola. So for hyperbola, we have also two foci, but then what is constant is the difference of distances from the foci. So we have one hyperbola. We have another hyperbola, and here is one focus. Here is another focus, and now now we have a property that if this is L1 and this here is L2, then L2 minus L1 is constant. Okay.
And this is for any point on the curve.
Hyperbolas. This is for hyperbola.
Oh, okay. Oh, yes, because the minimum distance between them is the constant.
Yeah.
Right?
Sorry, please repeat.
Is the minimum distance between them, like, yeah, so the minimum distance between them would be the constant, right?
No, we have hyperbolas come in pairs, so it's a conic section. So
yes, I meant the minimum distance between the.
And here we have one focus. Here is another focus. Now, if while for ellipse L1 plus L2, distance from one plus distance from other focus was constant. For hyperbola, it is a difference.
Yeah.
L2 distance from one focus minus distance from the other focus is constant.
Yes. So with a parabola, not a parabola, with an ellipse, the distance is equal to 2 times a.
Yeah.
But in here,
you can here also measure semi-axis like that. Actually, you can also hear 2a, but then 2a has a little bit different meaning.
Is it? Oh, yes, but a is the distance from the peak of the hyperbola to the center of the two lines, I think.
Yeah.
Correct or not?
I think it is a distance, probably distance from here to here.
Okay. And that's 2a.
Mm-hmm. Yeah. This is 2a, yes, this is 2a. Yeah. All right.
So it's similar to the major axis in a.
Yes, this is major semi-axis of A is major semi-axis of hyperbola. So distance between the tips of these hyperbolas.
Yes.
Is 2a. And also you have angles equal now, but now it is if you draw a line here and here, and then tangent, then it is between angle between tangent and the direction to the focus. Like one angle, the other angles is equal as well. I don't know if the figure is clear enough. Probably not. I might try to do it better. Okay, something like that. All right.
All right.
Now, regarding the foci and geometrical properties of conic sections. So each of the conic sections has foci, a pair foci. Parabola has one. Ellipse and hyperbola have two foci. And then we have equality of angles, and we have constant sum of distances. Now, one more thing. So as the formula for the conic section, a generic form of a formula for a conic section is actually a quadratic polynomial of x and y. So I clean this here now and write down the algebraic expression for the conic sections. This is also sometimes quite useful to know. So if we have factors a x square plus b xy plus cy square plus dx plus ey plus f, okay? And now if this is constant, this is the most generic form for conic sections. So by choosing A, B, C, D, E, F, you can obtain all the conic sections. Now, if B equal to 0 and A equals C, then what kind of curve is it?
Circle.
Circle, yeah, circle. Now, if A equals B equals C is 0, then what curve it is then?
Straight line. Straight
line, yes, line. Now, if B equals C equal to 0, then what it is? Parabola, yeah. But actually, you can obtain parabola. This is not the only possibility of a parabola. You can also actually have A, B, and C all different from zeros, but you have just the parabola. This is parabola which is parallel to x-axis. The axis is x-axis. But you can have y-axis, or actually you can have slanted axis. If you have slanted axis, A, B, and C are all different. The thing is that actually how you can distinguish when it is parabola, when it is hyperbola, and when it is ellipse, parabola, hyperbola distinguish. So this depends actually on A, B, and C. And what in algebra is called positive definite and negative definite polynomials. Basically, positive definite is such A, B, and C that for whichever pair of x and y you take, you have always positive number. So basically, it comes down to the discriminant of this thing. If now discriminant is positive if D equals B square minus 4AC. If this is negative, then there are no roots. If we equate this to 0, then there are no roots. So it is either positive always or either negative, but never 0. Then you have ellipse. Okay. If D is larger than 0, then you have hyperbola. And if D equal to 0, then you have a parabola. Okay.
Okay.
Okay. All right. So from time to time, there have been actually cases when it's useful to know this. For instance, so in one Asian physics Olympiad, you had actually it was a problem on electromagnetism, but actually it was some students had trouble solving it because they were not able to figure out shapes based on this thing here. Anyway, now let us come back to this. Now I'm going to clean this part here and go back to this. Now let me check. I forgot to. I was checking if I'm recording, but yes, for Zoom is nicely recording thing. Now. Now with all that explained, then please tell me how we are going to find the position of focus for this curve here, for this function here. Well, what is your suggestion? How could we find the position of focus?
You can take the second derivative, and you can get the radius at the topmost point.
Yeah. So the idea is to use the property of geometrical properties that the light beam converges to the focus. So this is curved like that. Now this is symmetry axis, which is x equal to 0. X equal to 0. And now we take a beam which is very close to it, to the symmetry axis. And then after reflection, it must go to the focus, okay? And now we want to find the position of focus, which means the point where it goes through this light here. This is our approach. Now, to that end, we need to know curvature radius, right? Oh, we can see that. Sorry?
Can the line be not near the axis?
Yeah, it can be not near, but then we have more calculation, more difficult to calculate. Because it is the easiest calculations if we take x very close to 0, and then it will work for any curve. So if you have like a parabola, you know that everything will converge into focus. But sometimes you might want to know just when there will be two nearby beams will converge to focus, and then you necessarily need to consider nearby beams. But here we use nearby beams just because it is easy to calculate. Now, you probably know from the optics that the distance to the focus in the case of spherical mirror is half of the radius. Do you know that?
Yes, yes.
Yes, you know. Okay, so basically we need to calculate the the curvature radius. How are we going to calculate curvature radius?
Reciprocal second derivative.
Second derivative, yeah. But now, if you think about the formula for second derivative, for the curvature radius, actually it is quite nasty expression. It is not an easy and nice expression. Because it includes also first derivative squared and some nasty powers. But the good news is that as long as the first derivative is very small, it is easy. So as long as f derivative is approximately 0, then curvature radius is 1 divided by second derivative. Okay.
Okay.
So I myself don't remember general correct expression for curvature radius. I would need to derive it or just look from the reference. But what I clearly know is that as long as first derivative is 0, then curvature radius is 1 divided by second derivative. So basically, we just need to take here second derivative. So second derivative is now g divided by v squared. So v squared divided by g. Okay. And curvature focal distance f is r divided by 2, which is v squared divided by g. And this is the distance from the tip, right? So this f over 2 is distance from the tip of the curve.
Mr. Why is it the radius divided by 2?
Okay. Curvature it is divided by 2. Okay, we have, let us consider a circle. And now we have one beam which goes through the center, and other beam which goes slightly sideways. And now this is reflected. Here is curvature radius. And now this is reflected from this surface so that these two angles are equal. Okay? But this angle is also the same. Okay? So this angle here equal to that angle here, which now due to reflection is equal to that angle. And so we have here isosceles triangle. This triangle here is isosceles, so that this side length is equal to that side length, because the angles are equal.
Yes.
Right? But we assume that it comes very close. It comes very close to this axis. So these angles are very small, and this angle here is also very small. And because of that, this part here is almost as long as that. So the distance from.
I have a question.
And so here is focal distance. And now you can easily see that focal distance is 2 times smaller than the radius. Yeah, question?
How do you know that it's an isosceles triangle?
Isosceles, how we know that it's isosceles triangle?
How do we know that the angle is the same? That's what I meant.
Let me draw it once again. Okay, now here is radius vector. And now due to reflection, light is reflected from the surface so that the angles between the surface normal are the same.
Yes.
Okay.
Yes.
On the other hand, since you know that from school probably that, this angle here must be equal to that angle here.
Okay.
And now you have here isosceles.
Because they're parallel.
Okay.
Yes.
But because this angle here is very small, because this beam was taken very close, so because of that, this here is actually very narrow triangle. which means that this length here is almost as long as this here. So this is almost as long.
Yeah, okay. So this side length is equal to half the radius.
And then you see that it intersects in the middle. All right?
Mr. Calder,
Yes.
Yes.
in the case of the parabola, why can we use the same thing?
Because we approximate the shape of the parabola with the shape of a circle. So if we speak in terms of reflection, if the shape is close enough, then the light reflects in the same way. And we just, if we speak about curvature radius, then it exactly means that we approximate the curve with a circle. Curvature radius is a radius of a circle which approximates in the best way the shape of the curve.
Mr. Calder,
Yes.
for ellipse, for example, I think this calculations is valid also.
Sorry?
The relation f is equal to half of the radius of curvature.
Yeah.
It's also valid. Is also valid in ellipse or any.
Yeah. Well, it is valid for any curve. So for any curve, you can calculate curvature radius. So what is curvature radius? Curvature radius, as the procedure of finding curvature radius is that if we have arbitrary curve, and now you want to know where is the, for instance, here you want to know what is a curvature radius. So then what you do is that you so how you calculate tangent? For tangent, you take 2 points and draw a straight line through them, and let this point here move towards the other one. So you start maybe somewhere here, so and then move it towards here, and it closes and closes. And when this point here approaches that point here, and then the line drawn through these 2 points is tangent. Okay, this is how we construct tangent. So you take 2 points, line through the 2 points, and then let 1 point move along the curve to the other. Okay, now how you can calculate and obtain the curvature radius. For curvature radius, you take 3 points. 1 point, another point, and one more point. And then you draw a circle through 3 points. You know that you can always draw points through 3 circles because this is a circumcircle of a triangle. You can always draw a circle through 3 points. And then you let these 3 points move, merge, like close, move towards each other. And then what you obtain is the circle. So in particular, the center of a circle is, so you take 3 points, one line, another line, and then you take meet bisector. Meet perpendicular of this segment here, meet perpendicular of this segment here, and where they meet here is the center of the of this circle, and here is the curvature radius here. Okay, and this is for arbitrary curve. All right.
Teacher, in the case of parabola,
yeah.
Now we assume we approximate it as circle, okay?
Yes.
Okay. What is the range that's going to be valid? Circle.
For circle, in the case of circle, there are so-called spherical aberrations. So if you take optical lenses, optical mirrors, they are all actually almost all the optical elements which you take, which you can have in lenses. They are actually spherical surfaces. Why they are spherical? It is because the spherical surfaces are the easiest and cheapest to make. But as you saw here, when I showed you how the center of the focus of a sphere is found, actually it is approximation. So if you take two beams very close to the going through very close to passing the center of the sphere, then yes, they merge at distance r/2 from the tip. So you can say that the focal distance is f/2. But if you take the beam which goes at a considerable distance, then it will intersect in a slightly different point. And so, all these spherical mirror, spherical lenses are known to have so-called spherical aberration, spherical distortions. And they are always constructed, and there is no answer at how close they can be. So the closer they are, the more accurate the result this approximation is. The closer the beam goes to the center, the more accurate it is to say that the focal distances are r/2.
I mean, for example, if you want to find the angle that gives you the maximum range, could you draw this?
But if we speak about parabola, then no worries. We just knew that all the beams merge into the same focal point. So in the case of parabola, because of the property that all the parallel beams converge after reflection into the focus, then there is no problem whatsoever. All the beams converge exactly into the focus. This is exactly the property.
We don't have here aberration like spherical.
Yeah, and no aberration in the case of parabola. It is just that we use the approximation of sphere to calculate the position. But once we found it, then this is valid for any beam. For any beam goes exactly through that point now. We just use the nearby point and the property of a sphere, formula from sphere to find this point. But once we found it, everything goes exactly through this.
Okay, now I understand.
Mm-hmm. All right, and now this is the focal distance, v squared divided by 2g. Now look here, the tip is at the height v squared divided by 2g. Okay, so actually we can see that if the distance of the focus from the tip is this, and the tip is at such a height, so the origin 0, 0 is the focus. So we learned now very useful property that this envelopes, the region where you can reach with your missile, the focus of it is the throwing point. Okay. Okay.
Okay.
And now we are more or less ready to solve different problems using that. And the first problem for you to exercise, I think you're going to soon to have a break, but before break, maybe you can solve it, is, okay, now, before I clean, this thing here, we managed to derive it, but it is actually useful to be able to more or less memorize this without a need to deriving it every time. Once you know it is a quadratic function, then actually how you can memorize it. It is quite easy. Namely, the tip is where you throw directly up. So if you throw directly up, the stone will go to height v squared divided by 2g from energy conservation law. It's very easy to memorize. Now about this thing here. This is the same shape when you throw a stone horizontally. when you throw it horizontally, it has the same shape here. You can, if you need, you can easily derive it any time if you don't remember.
I have a question.
Because y equals minus gt squared divided by 2 and x equal v times t, then you plug t into here and you obtain this term here. So that's how you can memorize this. Yes, question? Your question?
Would v in this case be as if it was like? Would it literally be as if you?
V is the starting speed.
Same one as. Okay. So it's as if a ball is thrown horizontally, but from a higher point.
Yeah. Here you throw horizontally, and it goes along the same shape as this term here.
Oh, I think I made the realization. Maybe it has to do with the energy. Like maybe you could prove this with energy.
This term here, no. Okay, this term here, throw just up and it goes to that height. Now, as for this term here, if you throw horizontal, x equal vt, which means as t equals x divided by v. Now, y equal to minus gt squared divided by 2, plug in t equals minus gx squared divided by 2v squared. It's the same term as here. This is just a way to memorize. Yes. Or you can also say that, okay, now let me clean here again. It is just what it means and why it is the case. Okay, here you have the envelope. Let us draw the envelope. Envelope is something like that. Now you now throw from the focus, and now depending your throwing angle, it goes like touching this. It goes touching this, and now it goes touching this. And now finally, if you throw horizontally, it just continues going down, and you can think of this touching that at the infinity. So that's why this shape here is exactly repeats the red shape here. Because they both are the parabola, the same straight parabola, just displaced each other by the focal lengths, and they are going to would be you can think of them as touching each other at infinity. More or less okay?
Yes.
All right.
Let's do. I think we should do some problems because.
Yes. Now the problems. And the first problem is using the geometrical properties of the parabola. Find under which angle you need to throw a ball from here to throw it as far as possible uphill. If this hill has slanting angle alpha, you throw at speed v, and what is the optimal throwing angle to throw as far as possible uphill?
Should we do this on our own first?
Sorry?
Should we start on doing this, or are we going to do it together?
This is exercise for you.
Okay.
I think you were all eager to try some program because I told you for a long time, but now you are eager to try something, right?
You will throw it abroad or downward. The maximum range.
So your task is to find optimal throwing angle so that you can throw as far as possible uphill if the hill slope is alpha. And the suggestion is that you use the geometrical properties of the parabolas. Okay?
Okay.
And there is one more hint. Suppose you have optimal trajectory throwing from here to here. Okay, and this is optimal trajectory. So B is as far as you can reach by throwing. Then the trajectory is actually reversible. This means also that A is the farthest point you can throw from B with the same kinetic energy. Okay, if you have V naught here from energy conservation law, here speed is V square is V naught square minus 2gh. Right, this is h. Okay. Now, one situation, optimal throwing from here with speed V naught. The other situation is optimal throwing from here with speed V. Trajectory is the same. So if trajectory is optimal one way, it is also optimal for throwing other way. This is also a small hint how you can how to solve this problem. All right.
Okay.
Now, what shall we do? I think you have also now break time.
2 minutes after 2 minutes.
Sorry, two more minutes to go. Do you think you can you will be able to solve it with 2 minutes?
Maybe if we work fast.
Okay. Okay. Try.
I got something, sir.
Yes.
The angle is going to be 45 minus alpha over 2.
Okay.
I got the same. I got the same also.
Two of you got this result. That might be even correct. So what about the others?
I am solving a system of equations, I think. It might be the
But
same.
you are not supposed to solve system of equation. You are supposed to do it geometrically.
Yes, geometrically.
And you won't have system of equation if you do it geometrically, I think.
Oh.
Does the break start now?
Yeah, break starts now. So we'll solve it together after the break.
I get the same.
You got the same? Okay. But we'll be solving together after the break.
What is the What does it want?
Once again,
What is the problem? What is the thing you want us to find? The maximum distance?
optimal throwing angle. We can say that there are actually two possibilities. Whether you give this angle here or you give this angle here, whichever.
Okay.
-45 minus alpha over 2 is small, right?
Yeah, 45 minus alpha 2, alpha over 2 should be a small angle. How are you? Are you back?
Yes.
And solving still, or shall we do it now together?
Let's go.
Together.
Okay, let us do it that way, that some of you still want to try it by yourselves, and some of you already solved it and want to do something else. Now, I am giving you the problem from IP 2012. Oh, no, before that, I give you a problem that we have here a house, which has roof like that. This is a side view of the house. This here is A, this is B, this is C. Okay. Now, you throw a ball from the ground level. What is the minimal speed to throw over the house? Okay. Is it clear?
To reach the other region, or what?
So the task is to throw a ball over this house with minimal possible speed from the ground. What is minimal speed to throw over this house? Where the side length it is trapez side cross section, and side length is A, B, and C respectively.
From the
ground level. You find optimal place to find the optimal place to throw and throw with minimal speed. All right.
Hello.
Yes. How are you?
Oh, you gave us a new problem.
We have still this problem here. Some of you wanted to solve it. And then
Yes.
I gave another problem for those of you who already solved it. And the other problem is that you have a house, and then
I know the problem.
yeah.
Yeah, I already know the problem. I think we did it before.
You solved it already?
No, before, like a long time ago.
Uh-huh.
So I think I remember the problem.
Uh-huh.
You have
Okay.
something going from the right to the left.
The task is to find minimal speed to throw over. And the hint is also to, I suggest try solving it using the geometrical properties of the parabola.
circada.
Yes.
Is it square root of G times A plus B plus C?
Yes, that's correct. So, shall we solve some problems now together?
Okay.
Shall we solve this problem here?
Let's go.
Tadek,
Yes.
how about you? Shall we solve it?
Yes, I think that would be good.
Okay, so the idea is that if we draw vertical line here, okay, if we draw vertical line, this point here is optimal trajectory goes to here. So this trajectory at this point here must be tangent to the envelope parabola. Envelope parabola goes something like that. And so this means that this trajectory here must be tangent to that one here. Okay, something like that. If we throw to the optimal point, then it must be tangent. And sorry?
Why, if it is optimal, it must be tangent?
Oh, because for any point inside, if you throw with the same speed here, you have two different possibilities to throw through, and none of them is optimal because optimal points, the farthest point where you can throw is on the black line. If it's inside, it is not optimal to throw that. So if you throw from here optimally here, this point here must lie on the black line. Once it lies black line, the red line must stay always inside the black line. So the only possibility is that it is tangent. If it is not tangent, it would extend outside.
Yes.
Okay. So it is tangent. And so if we apply the optical property of parabolas, that straight line drawn from here, upon reflection on the black line goes to the focus, which is a throwing point here. We can just as well let it be reflected from the red line here, because red line here is also the same slope, and so it reflects in the same direction. So if we reflect this vertical line from this throwing trajectory, red parabola, it goes here. Now, as mentioned before, throwing from here to here, the same trajectory here is also optimal. So, which means that now, similarly, if I draw a line here, it is reflected from the red line into here. Okay. So what does it mean? It means that these two angles are equal, and these two angles here are equal to each other, but they might be different from each other. Okay. So let this angle here be beta, and then how is beta and alpha related to each other? Beta and alpha are related to each other in such a way that 90 degrees plus alpha plus 2 beta equals 180 degrees. From here, we can conclude that 2 beta equals 90 degrees minus alpha, and beta equals 45 degrees minus alpha over 2. And here you are. Okay. Clear to everyone?
Yes, it's clear.
Mhm.
Yes.
Now, regarding this problem, would you like me to do this as well now?
No, just a moment.
You want to try this, okay?
Yes,
Once you want to try it, I can give one more problem for exercise. And this is IPITSO 2012 problem. You want to throw optimally from ground to this topmost point here. And then with minimal possible speed so that it will not bounce off or just flow directly and fall on, onto this topmost point. And what is the minimal speed? If this radius is here r capital. Okay. And first you need to sketch the optimal trajectory, and then you need to calculate what is the minimal speed. All right.
All right.
Circle.
Yes.
Is it square root of 2gr 1 plus square root of 2?
Once again,
Is it square root of 2gr times 1 plus square root of 2
2gr
times inside the square root times 1 plus square root of 2?
I'm afraid I still didn't get square root of 2gr and what else?
And also inside the square root, multiply this by 1 plus square root of 2.
Like that?
Yes.
But unfortunately, this is not correct.
So Kaga,
Yes.
is it the same as what I said, but instead of 1, 2?
Sorry?
Is it square root of 2gr times 2 plus square root of 2?
2 plus, no, 2 plus, not 2 plus 2 square root of 2, no. Still no.
Okay. So Kaga,
Yes.
is it square root of gr times 2 plus square root of 2?
No. GR and what?
Times
Like that?
2. Yes.
No. This is not correct. Guys, tell me if you have solved this problem here.
I couldn't.
Tell me tell me yes if you have solved it. This problem here. Anyone else apart from Al-Qassem?
There is no one.
Muhanna, did you solve?
No, I have some lengthy calculations.
So you're working on this. You're working on this.
Yeah, but I think we have spent a lot of time, so maybe it's a good idea to solve it together.
So you suggest us working together. So what about the rest of you? Is it okay you start doing it together?
Yes, yes.
Okay.
Yes, let's solve it together.
Okay.
Yep.
Now here we need to work in many steps. First is to figure out that in case of optimal trajectory, the optimal trajectory needs to touch both this point here and this point here. Is this obvious? That optimal trajectory needs to touch this corner here and this corner here. Suppose it touches only one corner, then we can step back and then our trajectory will not touch none of them, and we can decrease the speed, right? Little bit. We can we step back. Now it is not touching neither of the corners, and then we can decrease just a little bit the speed so that we'll still go over the building. So because of that, it is clear that it must touch both of the both corners. Now, if so, then the optimal trajectory actually is also optimal trajectory for throwing from here to here, or from here to here. And if so, then our trajectory, optimal trajectory, goes like that. And then we also know that this point is the focus of the envelope trajectory. It is the focus of the envelope trajectory, which goes like that. Okay.
Why it will pass
because this is, if we throw from here to here, so this is optimal trajectory for this throwing. So this point must lie on the envelope parabola.
Yes, why?
Sorry?
Why it must lie on the envelope?
Because this we throw optimally from here to here. If we throw optimally, the target is at the envelope parabola.
So in general, it is a general rule.
Yes, because everything, if you throw optimally, your trajectory is such that the target is at the envelope. Otherwise, you can find you can decrease the speed so that the envelope parabola will contract, and you will be still able to throw. Suppose you throw from here to here optimally. Okay, and suppose from the contrary envelope parabola, so if envelope parabola is smaller, then of course you cannot throw it. If envelope parabola is like that, you cannot just throw it. If it is larger, like that, and if your trajectory goes optimally from here to here, suppose envelope parabola is larger, then and your trajectory goes like that. But your trajectory must touch actually as this one here. But then you can, if you decrease now the throwing speed, the envelope parabola will contract. And if it contracts and this point here still remains inside, then you can throw with your smaller speed, which contradicts the assumptions that the trajectory is optimal. Did I make myself clear?
Yes.
Okay, so if you throw from A to B optimally, then B is at the envelope parabola. But now it is now this point here is on the envelope parabola, and this is a focus. And now all these points on this black parabola satisfy condition that that B prime and C prime, B prime plus C prime equals B plus C. Due to the property of parabola.
Okay.
Yeah, and so which means that basically you can with the same speed because the envelope parabola is defined by the throwing speed. So with the same throwing speed, you can also throw over this building here. If you can throw over this building here, this, then you can also throw over this building here as long as B prime plus C prime is B plus C. Because the 2 points lie on the same envelope.
And this is for any point, right?
Yeah, so any point on here, it is if you can throw over this building, you can go throw over this building, and you can throw over this building.
Yes.
Okay.
So then,
basically, the question is what speed is needed to throw over this building? With the height, so that A plus B prime plus C prime equal double height here. So but we can remove primes because okay, B prime plus C prime is B plus C. So you can, with the same speed, when you throw over this building, you can throw over a building of height H equal A plus B plus C divided by 2. So we can now write V squared divided by 2 equals G times H equals G times A plus B plus C divided by 2. So that V is a square root of G times A plus B plus C.
So how did you get this B plus C is equal to 2H?
Sorry?
How did you get A plus B plus C equal to 2H?
Okay, well, basically, we can maybe actually considering here other buildings actually was not necessary. This was just one way of doing it, but we can also do it in such a way that for the envelope parabola, we know that the tip of the parabola is if tip of the parabola is at the height h, then b squared divided by 2 equals gh, is the height to which you throw. And now And now we consider because of the property of parabola, if we and due to the fact that this is the focus of the parabola, due to the fact that okay, let me draw another figure. Let me draw another figure, or maybe. Let me do this one.
Future,
Yes.
if we use the directrix, I found 2h plus a equals b plus c.
Okay, let me just because I was explaining you the solution. Let me explain it once again what I was planning to do, and then I'm listening what you were suggesting. So we have our building, and then we throw from this point here, and then we have envelope parabola, which goes like here is throwing the parabola. We throw like that, and then goes envelope parabola because I throw from this point here. So this is the focus of this this envelope, and envelope goes is touching also here. Envelope parabola goes something like that here now. Okay. Now this point here lies on the parabola envelope, and now we consider two. Now we consider the property of envelope for 2 points. One point is here, and the other point is here. Now, if this is B and this is C, for this point here, the sum of distance of the point on the envelope from the focus plus the height of this given point is B plus C. For this point here, P. And here is P prime. P prime. And for P prime, the same thing is going to be, this is for point P, distance to the focus plus height. And due to the property of the parabola, this remains constant for any point on the parabola, in particular for point P prime, the tip of the parabola. And here it will become, let this be here height h. Okay, then this becomes h, height, distance from the focus, plus height, h plus a. Okay. This is for P prime. Distance of a point from the focus and height of the point. Distance of the point from the focus and height of the point. From here we have 2h equals B plus C minus A. And so from the ground level, the height from the ground level, h prime equals h plus a. And from here, h is that one here divided by 2. So it equals b plus c minus a divided by 2 plus a equals b plus c plus a divided by 2. And so we found the height of the parabola, of the envelope parabola. And we know that the envelope parabola has height which equals to the height from to which ball will fly if you throw it straight up. And now from the conservation energy conservation law, just we can throwing velocity here, the throwing here comes from energy conservation law, but from the energy conservation law, you can directly relate it to the kinetic energy for throwing from the ground. So then you can see that from the ground, speed needed is v squared divided by 2 equals g times h prime. and we recover the same result. From here, V equals square root of G multiplied by A plus B plus C. Okay. So the main steps are finding the height of the envelope, H, from the tip of the building, from the highest point of the building, using the geometrical property of the parabola. Height plus distance from the focus are constant. We can relate it, knowing this distance for P, we can find it for P prime as the top of the tip of the envelope. Once you know now the height of the, from here we can now find the height of the tip of the envelope, but the height of the tip of the envelope is directly related to the kinetic energy of the ball. So it's just the height from where ball will fly if you throw it straight up. And because of that, knowing H prime, you immediately obtain the speed needed to throw. All right?
All right.
Clear to everyone?
Yes.
Shall we go to the next problem then?
Yes.
Okay.
And the next
You hear
problem,
me?
yeah.
Okay. Okay.
The next problem was throwing optimally to the topmost point of spherical building. And here the trajectory will.
You need time to solve.
Sorry?
Are you going to solve now? We need time.
We give you time, but just to make it easy a little bit for you, I draw you the optimal trajectory. So optimal trajectory is going like that. It is going to touch similarly to here. So it is going to touch at certain point and then like going like that. Okay, this is how the optimal trajectory looks like. And now again, please, and it is touching of obviously it is touching the spherical building at this point here, at some point. We don't know exactly yet which point it is. So probably it is going to be your first task to find. Okay, let us see if touching point is here. So what angle here alpha is? So you can try to figure out what angle alpha is.
Mr. Calder, you want the minimum velocity required to let's say pass the topmost of the sphere or the whole sphere, because according to your figure it will hit the sphere later on.
It will. I throw from here and it hits the topmost point.
Yes, that's required.
Yes, that is required. So minimal speed to throw to here, to the topmost point.
Okay.
And the first task is to find what is the angle alpha, the angle at which the optimal trajectory is touching the sphere. Once you know alpha, the rest is easy. Yes.
Is alpha equal to 60?
Sorry?
That's alpha equal to 60.
Yeah, alpha is 60. Now, once you got alpha, you can continue to finding minimal speed.
is v equal to square root of 9/2 gr.
Yeah, something like that. So Al-Qassem, you want something else to do now to exercise?
Yes, yes.
So now this is a Hungarian problem. You have water filling a cylindrical vessel, and then you have a lot of holes here. And then from each hole, you have different trajectories. Okay. And then you're asked about the shape of the envelope of these trajectories.
Okay.
The shape of the envelope. Okay.
Okay.
Mr. Yan,
Yes.
Mr. Kalba. So in the other problem, in the ABC problem, when we did the thing where we looked at parallel lines or vertical lines,
Yeah.
how did we know that like which points did we know, like did we take as the focal point? How do we know where to take the focal point?
Okay. The throwing point is the focus of the envelope parabola. So we know that if we throw from here, then this point is the focus of this envelope. And that's what we wrote down here.
Okay, so, and then any point that goes to the parabola, and then we can just use the theorem where the distance between, like we can say that the ground to the point, and then the point to the focus, it's always the same.
Yeah. Yeah.
Mr. Kalda.
Yes.
Can we apply the same thing here? The first touching point to the topmost can be considered as the optimal trajectory.
What do you think?
I think it should be, because you want
because
just to reach the topmost.
Throwing is reversible. So if you can throw from this point here or to this point here, you can also throw the other way around. If you throw here from this speed, it will go down that way. And it is optimal in the sense that if you take it smaller speed, it will collide with the sphere, and yeah, so this is touching. So which means that if you consider throwing from here, so this point is on the envelope. If you throw from here, this is focus, this is on the envelope.
All the same thing. If you throw from the middle of the sphere, the topmost will be in the envelope.
Sorry, once again?
I mean, if you launch from the middle point,
yes,
to the topmost,
yes,
the topmost what should be in on the envelope also.
So you can throw from here, and this is on the envelope. If you throw from here, this is on the envelope, because this trajectory, this piece of trajectory is optimal for throwing from here to here, and then the other way around.
Okay.
You can think in that way that okay, if you can throw from here to here, you can also throw the other way around. So we can also ask the other way that what is the minimal speed to throw from the top to get the ball down? And now in that case, it is clear that the trajectory must touch this, and the touching point must be on the envelope, because if it is not on the envelope, if envelope goes higher, then your trajectory can also bypass the sphere a little bit higher, and then you can just decrease the speed. So from here it is clear that the touching point must be on the envelope.
Teacher,
Yes.
is the Vmin going to be the square root over, sorry, the square root of 9gr over 2?
Yeah, that's right. So shall we solve it now together?
So Karda,
Yes.
is the envelope the straight line?
Yes. Did you show it?
Yes.
Under which angle it goes?
What?
Under which angle it goes?
It's, I think, horizontal.
Sorry?
You mean and which angle it goes up?
Which angle does it form with the horizon?
Oh, you mean the line? I didn't find it yet. I think 45. Yes, 45.
Yes, that's right. Al-Qasim, you want another problem?
Yes, yes.
Can we solve the circle problem?
Yeah. Before we solve, I give Al-Qasim another problem. So we have a slope and we have a perfectly elastic ball which starts bouncing. Okay, and now each of these parabolas has a focus. This has a focus f2 and so on. So the question is, the task is to find a curve on which these foci lie. The angle here is alpha. And you need to find curve where the foci lie. All right, but now we're going to solve this problem, right? The sphere problem.
Yes.
Okay. So first thing to notice. So let this be the tangent point. Now, because trajectory is tangent to the ball and envelope is tangent to the trajectory, so it means that the envelope is also tangent to the sphere. So if we draw a vertical line from here, it must go to the topmost point here. Okay?
Why is that?
So, upon reflection on this surface. So if we have if we have center here, so this angle and that angle must be equal. Okay?
Why?
If we draw vertical line, it is reflected by the surface of the sphere to the topmost point because topmost point is the focus of the envelope and P is on the envelope.
Oh, so what you said is that you kind of reversed the. You reversed it so that it's as if it starts from the top.
Throwing from here, yes. I come throwing from here, so this is on the envelope. Okay, now this is on the one hand. Now let us draw here triangle. Now this angle here obviously equal to that angle here. Okay?
Okay.
And then this side length equal to that side length. So this is isosceles triangle. Once it is isosceles triangle, then this angle here is equal to that angle here.
I have a question.
Yes.
So why did you say that the? I think if you know that two angles are the same. Oh, never mind.
Okay. because this is radius, these are equal, so it is isosceles triangle, this angle equal to that. But this angle equal to that, and that angle to that, so all the angles are equal. So each of them is 60 degrees. Okay?
Okay.
Wait, Mr. Kad, you said that the two angles are the same
Yes.
from the reflection, but why the normal is the same as radius?
Tangent.
Yeah, so this is surface normal. If beam is reflected, it the angles formed by the surface normal before and after are equal. This is property of reflection.
الانفلوب tangent حق الكورة.
Yeah, because if you throw from here, trajectory is tangent, envelope is tangent to this curve.
Okay. Okay.
Okay. Now, what next? No, next, we need to calculate the height of the envelope. Envelope goes something like it is tangent here and goes to here. This is envelope. Okay. Now we need to calculate the height of the envelope, and what we do is we write down now for 2 points on the envelope the property that the distances from the foci and the height are equal. So if here is h, from the ground level the height is h plus 2r. Okay, so here we have like that. Now we take this point on the envelope, and then we have h is the plus 2r is the height of this point above the ground level, and h is the distance from the focus, okay, for this point here. And this must be equal to the same thing for point P. And for point P, the height above the ground level is 1.5 r. This is r, and we still need to have half r. So it is 1.5 r is the height above ground level, and then distance to the focus is another r. Okay?
Okay.
And from here we obtain that 2h equals 0.5 r. So h is 0.25 r. All right. So now we know that we need energy so that if we corresponding to potential energy at the topmost point. So our energy from ground level must be V squared divided by 2 is kinetic energy for unit mass, must be equal to potential energy at the top of the envelope, which is now height from the ground level is 2.25 r. 2.25 r multiplied by g. Okay, so V equals square root of, and as you correctly told, 9/2 times g times r. All right.
All right.
So once you know the angle, then it's just like the problem before, right?
Yeah.
Yeah.
Exactly.
Now for the water,
For this, okay.
yeah, the container.
What was the
Would you like to try it yourself or want me to show?
Yes, we want to try, but what is the problem? Could you say it again?
Okay. Here is you have a cylinder is filled with water, but there are a lot of small holes on the side wall. So water is streaming out of the side walls, and each of them forms a parabola now. And the question is, what is the shape of the envelope of all the parabolas?
another parabola?
No.
Do we have something like the height h for the water, or just like that?
Sorry?
Are we given something?
You have everything what you need to have.
You have what?
Nothing given, just the shape of the envelope you asked. Just say that, okay, height of the 4 base h if you want to have it, but
Okay.
So how are you doing? Any success?
Not that much. I'm still trying to derive the velocity at a height. I don't remember it.
Ah, then that is easy.
Just a moment, sir. Can we take 1 minute more?
Yeah, sure. Just to help with the speed. So if here is pressure P, then if
Yes.
water goes out from Bernoulli law, you can say that if here you have pressure P is rho GH, where H is the height from the water level. Then Bernoulli law
Yes, this
says
is
that P plus rho V squared divided by 2 is constant. Inside V is 0.
oh, okay.
You have rho GH plus 0 equal, now outside pressure is 0. Well, precisely atmospheric, which adds up to both terms. So we would say that P, P naught plus rho GH, and outside is because here water is in contact with air. So it means that
Yes.
there is free surface, which means that pressure inside water is atmospheric. So it equals to P naught plus
not.
V squared over 2. So P naught cancels away, and we obtain V equals square root of 2 GH.
Okay.
Teacher,
Yes.
I got an inequality.
Yeah.
Because I have a square, I don't know how to put the signs. Can I tell the inequality?
I just the line which is the envelope, so just equality. Y equals a function of x, for instance.
Minus h plus h.
Yeah, something like that. All right, so you got the answer?
What?
Okay, very good. Anyone else?
Okay, I will tell you the inequality. I have squared. Then if I take the square root, can I put the minus sign? Because I know it will be the slope will be negative, not positive.
Yeah.
So I put when I take the square root, because I have
Yeah, you select the correct sign of the square root. Yeah, that's what you need to do.
Okay. What is the next problem?
Next problem was, now I cleaned it, but it was,
And also no break.
you have here a slope of angle alpha. You let elastic ball fall, and then it starts bouncing. And each of those parabolas have somewhere a focus, F1, F2. And now your task is to find the line where those foci lie. Curve on which foci lie. Okay?
Is it given that it is a straight, or I have to prove, or
If it is straight, you need to prove, of course.
what?
If it is straight, then of course you need to prove that it is straight.
Okay.
Yes.
Give a hint of the ball problem.
Sorry?
You give me a hint of the ball problem.
I didn't hear. Sorry.
A hint for the ball problem.
You solved this problem?
Yes, for this problem. A hint.
Sorry?
A hint.
You need hint. Okay. Well, of course, there are different ways of doing it, but the easiest, the simplest way is using geometry and directrix. So the first step is to figure out where are the directrix of these trajectory parabolas. Each of these trajectories is a parabola, and each of them has a directrix. And the first task is to figure out where are the what is the directrix.
Break now, sir, or what?
Sorry?
Break.
Yeah, now break, 10 minutes.
مستر كالدا. شباب جايز في أحد حل حق الماي؟
يب.
وش الجواب؟
طلع
شيك.
وش طلع لك؟
5/4 اكس نيجاتيف طبعا. سلوب.
ماني متاكد من المعامل بس انه يطلع ستريت لاين.
يب straight line going down slope. اوكي مسألة. سويت ديريفيتيف. متى يخلص الورق؟ اوكي 5 دقائق. اروح اجيب اكل.
كيف
Teacher,
Yes.
could you say the problem again?
Sorry?
Could you say the problem?
Explain the problem.
Just say it.
Solve or say
The bouncing ball.
bouncing problem.
What's going on?
So the elastic ball falls and starts bouncing on the surface. Now, each of these pieces of trajectory has its focus. Because it's parabola, a parabola has a focus. Now, F1, F2, and so on. Your task is to find on what curve lies the foci.
Just I have just reviewed the name of the curve.
Yeah, it's a formula for the curve. Formula, not just name, but specify exactly what how to draw the curve.
Okay.
For the water container,
Yes.
it's a straight line, right?
Sorry?
But for the container, water container,
Yes.
where you have holes inside of it on the side. Do you have the slope? Because I got the slope for it, and I want to make sure.
So you can, so it is straight line, yeah, this line.
Yes, I got a straight line for that, and I have a slope.
What is your slope?
5/4.
5/4.
Negative, of course.
Oh, sorry? No, not 5/4.
Oh.
Slope is not 5/4.
Oh, maybe it should depend on the density.
No. In the speed, there is no density. How come it can depend on density?
True.
Density cancels out because gravity and inertia both are involve density.
Teacher,
Yes.
does the collagen elastic?
Once again.
The collagen elastic with the plane.
Elastic collisions, yeah, perfectly elastic. All right, guys, shall we solve this problem here?
Yes.
Okay. So now we have one possibility is to solve in the same way as we found envelope before. We have already found one envelope with you, right? It was the envelope of the trajectories when you thrown from the origin. Now we say that if we repeat exactly the same way, okay, here is let us now draw our coordinate zone. That this is water level. Here is y downwards, and x is horizontal. Okay. And now we consider one hole at height h. Okay. And then it is a shape. And now we consider coordinates x and y, and ask if we find such h that the trajectory goes through exactly the same way as we worked before. Before we parameterized with angle alpha, but now we parameterized with height h. Okay. So that now the trajectory is going to be x equals v times t. From here, t equals x divided by v. Y equals h plus gt squared over 2, g over 2, and x squared divided by v squared. This is a trajectory. But now v squared is 2gh. So that this guy here is further going to be h plus g cancels away, right? H plus x divided by 4 h x squared, like that. And now we consider this as an equation for finding h. At which height h the water stream will need to start in order to go points through x and y. So now this is going to be our quadratic equation for h. So let us rewrite it. H squared minus yh plus x squared divided by 4 equals 0. So that now our discriminant is going to be y squared minus 4 times x squared divided by 4 equals y squared minus x squared. And critical case discriminant equals 0 is y equals x. Y squared equals x squared. So y equals plus minus x. And now we just see that if we look at the slope on the right hand side, we need to take with minus sign, so y equals minus x. All right. This is now just using the same approach as we did before, as we found previous envelope.
Yes, it's my method, the same as my method, but I found the mathematical error. So
okay, but now let us try solving it in a different way. Let us now the question is if we can solve it using geometry. And in that case, we would like to first figure out. So we have a lot of parabolas, but where is the directrix of these parabolas? We start with directrix. Now we have plenty of subtasks. What we are going to do? This was fairly easy. Yeah, once we know what you're going to do, this was fairly easy. But now, now we ask, where is the directrix of this trajectory here, or more generally, if you throw here a ball and it goes like that, where is the directrix of this parabola?
you can take it anywhere.
Sorry? Directrix. No, there is only one directrix.
Oh, the directrix. Oh.
Yeah. There is only one directrix, and we ask where it is.
At y equals v naught over g.
Yeah, well, someone of you already knows the answer, but let us go and take our time. So it is a point from where focus is at the same distance as the directrix is to, if here focus is here, directrix has equal this distance to the other side, because distance of the point from the focus equals the distance of the point from the directrix. Now, but we know that, let us consider now throwing, as a problem of throwing a ball from this point here with the same kinetic energy as this one has. So now, if we throw from here, we can have different trajectories going like that. And if it goes up, then it goes straight down. And now you have envelope. And we know that envelope has exactly the same shape as this curve here if it's thrown horizontally. So this envelope shape is exactly the same as the trajectory shape. This we already discussed before.
Okay.
And now the distance of the envelope, focus of the envelope, we already know. Envelope, focus of the envelope is the throwing point here, which is the topmost point of the red curve. So this is a focus, and this is the distance of the black parabola from the focus. But red parabola has the same shape. So the distance of the focus of the red shape from its top equals is the same as that of the black curve. So black curve has distance here, so red curve has distance here. And we can see that the top of the envelope is at the red curve at exactly the same distance as the focus of the red curve. So it means that directrix goes through the top of the black curve, which is the point where ball would go if you throw it straight up with the same speed.
I didn't understand it.
So the conclusion is that the directrix of the parabolic trajectory is a horizontal line at the altitude where the ball would go if you throw the ball directly up. This is a lesson. We derived it based on this topmost point of the red curve here, but obviously it's valid for any point here because, well, directrix is characteristic of this red curve here, and it's just a line where the potential energy equal to the kinetic energy of where the potential energy equals to the full energy on this red trajectory.
Mr. Calda.
Yes?
I didn't understand. What did you do?
Oh. I was finding where is this directrix of a parabolic trajectory. I throw a ball here and it goes around parabola. And I was asking, where is the directrix of that parabola? Okay? Is this clear now?
Yes. And then how did you find it?
Okay. How did I find? So in order to find the directrix, I consider it's the topmost point of the trajectory.
Mm-hmm.
And now I imagine myself throwing from the topmost point of the trajectory ball with the same kinetic energy which the red one has. With the same kinetic energy.
Mm-hmm.
And then this problem has envelope, which is a black line here. But that black line here, we learned before that it has exactly the same shape as this red curve, because we learned that the shape of the envelope It's the same what trajectory would have if you were to throw ball horizontally. Here you throw ball horizontally and it draws a red line. So the envelope has exactly the same shape. Okay? So the problem of
How does that happen?
For the problem of throwing ball from the topmost point of the red curve with the kinetic energy of the red ball, the envelope has the same shape as the red parabola. This we discussed before. I explained this as a method how to memorize the envelope, formula for the envelope. That the shape is exactly the same what we would have if you were to throw horizontally.
Okay.
Okay, so the envelope now has exactly the same shape as the red curve here. So which means that distance of the focus of the black parabola is the same as in the case of red parabola, because the shapes are identical, the relative position of focus is also the same. But we know that the black curve has parabola situated exactly at the throwing point, which is the top of the red curve. So the distance from the envelope to the top is the focal distance from the black curve to the focus. And this must be the same for the red curve. So the red curve has focus exactly at the same distance, which means that the top of the black curve is situated at the directrix of the red curve, because distance of the top of the black curve from the top of the red curve equal to the distance of the focus from the red curve. This definition of the directrix. So directrix goes through the top of the black curve. Still following?
Yes, yes.
And so this means that, but then we know that the altitude, the height of the top of the envelope is the same how high the ball will go if you throw it horizontally, which means that it is a point where the potential energy equal to the full energy of the ball. And that's a conclusion, that directrix of a parabolic trajectory is a horizontal line which at the altitude where the potential energy equal to the full energy on the trajectory. Okay, let us write this. Directrix.
Okay, teacher, this is related to which problem?
I am giving a second solution of this water stream problem, but we can also apply it here. This will be needing here as well. Directrix of a trajectory at the altitude at
Teacher, I have an answer for this problem. It will be parallel to the plane, to the inclined plane.
Sorry, not parallel, not parallel.
Not parallel.
At such altitude that potential energy on directrix equals full energy on trajectory. Directrix of a parallel trajectory has potential energy equal to the full energy on the trajectory. Very easy, very simple. So everyone got the point? Everyone happy?
Yes, yes.
Shall I move on?
Let's go.
All right, now I clean this part here because I need space. And now consider a stream of water. And then now it is clear that this line here is directrix. Is it clear that this line is directrix? Because here v square equal v square divided by 2 equals GH. It's the water stream at this point when it goes out. So if you were to direct it up, it would go just reach this top level, water level. So which means that the water level gives you the directrix. All right.
All right.
And then, which means that focus of this trajectory here is, if this is h, now focus is at another distance of h. And now let us draw a horizontal line here. Okay. Now, this intersection point is at the height of 2h from the water level, from the directrix. And because of the property of parabola, so it must lie at the distance of 2h from the focus. So the length of this horizontal line is also 2h. Now we see that if we draw a line at 45 degrees, it goes through this point. So at least this trajectory here, arbitrarily drawn trajectory, has a point on this straight line. Now the question is if this trajectory is envelope or not. So if we now can show that this line here is tangent to this curve here, then it is envelope. Because then this curve here is beneath this straight line, but this was arbitrarily drawn line. So in that case, this line here is touching the line at 45 degrees, and it is curved downwards. So this horizontal, this inclined line must be the envelope. Now, how can we see that this line here is touching the line drawn by 45 degrees? Well, this is also fairly easy because now we know that we have the property of the ellipse. So because now vertically drawn line, when reflected from this ellipse, must go to the focus. So if we draw here, it must go horizontally here. So this angle here must be equal to this angle here, but this angle here is this angle here. So it is 45 degrees. So the tangent of the trajectory is 45 degrees also. So we can see that this line here is the envelope line. All right. Satisfied?
Okay, teacher, how can we know if they are this angle as the same as the upper angle in the triangle up before you know if it is tangent or not?
Okay, so my steps are were as follows. Let me repeat my steps from the beginning. Now, here is what it's the directrix. Here is water level. Now here starts arbitrary water stream. Goes like that. Now, now I conclude that I consider focus. So this is H to the focus. Now I draw a horizontal line at the height through the focus. I draw a horizontal line through the focus, and then because this is here a focus, I know that if I draw of this parabola, I know that if I draw a vertical line, it must be reflected by this parabola to a line which goes through the focus, but this horizontal line. So since this is reflection, this angle must be equal to this angle here. On the other hand, if I continue this line here, so this angle here, of course, equal to that line angle here.
Yes, here.
So this angle equal to that angle, each of them is 45 degrees.
Okay. Because you know it is 45, and then you make.
Yeah, it is 45 degrees. On the other hand, yeah, because this is 2h and this is focus. So a distance of this line here from the directrix is 2h. So distance to this focus is also 2h. So so this line is also 45 degrees because this is 2h, this is 2h. So a line drawn from this point here, from the corner of the water, is 45 degrees. Tangent is also 45 degrees. So that completes the proof.
Okay, now clear.
All right, and now I'm ready to go to this problem here.
No, 5 minutes, after 5 minutes, please.
So everyone now is clear what the problem is. Well, just in case, once again, we have inclined surface, slippery surface, angle alpha. A ball is bouncing. We release it here at certain height, and it starts bouncing. Each of these curves here is a segment of a parabola, but these are different parabolas. Now each of them has a focus. The question is, what is your task is to find curve on which all these foci lie. Okay. And the first thing is to consider directrix of these parabolas. But there is one more trick actually to it. And namely, guys, what do you think? What is the envelope? Can you draw, well, not envelope, but okay. If we consider the height of these parabolas from the inclined surface, so this height here, what is it equal to? Here is angle alpha. We release at height h, so this is why we release it. Now I am
it's always going to be the same, right?
What is the height here? Yes?
It's always going to be the same, right?
H over cosine alpha.
Yeah, it is h times cosine alpha. Why it is h times cosine alpha? Can everyone of you see that it is h times cosine alpha?
Yes. I think if we rotate it so that the slope is like horizontal, then it will be like you have separate accelerations for the x and y.
If we rotate it, then we have a g horizontal, g times cosine alpha, and we have horizontal g times sinus alpha. G cosine alpha is vertical component of gravity field, and g sinus alpha is horizontal. And now this way it is always like bouncing up and down like to the same height, but this gives acceleration in horizontal direction. So it will start now bouncing here like that, long and longer jumps. But the height is the same always because you can separate vertical motion and horizontal motion. So basically, you can here separate motion perpendicular and longitudinal, and perpendicular motion is just periodic motion up and down.
I think that if we separate the axis then we can calculate the radius of curvature at any point really easily.
No, this is a bad idea. Don't do that. This is my friendly recommendation. Don't do that. My friendly recommendation, or otherwise, you can say hint, is that now consider this line here. We draw from this line, which is touching all these parabolas. And this is going to be parallel to the surface because the height is always the same. And then on the other hand, consider directrix, because kinetic energy is no energy loss, kinetic energy equal to the potential energy at this point here. So directrix line is just a line through this here. This is directrix line.
How the directrix line will not be, how it will, the parabola,
Sorry?
if the parabola, sir, is, if the maximum point for each parabola is lie on the black line, how the directrix will not be parallel to them?
No, well, these are each of them is a parabola in normal gravity field which is downwards. If you consider this way, these things here now are not parabolas axis which is down, but axis. These are parabolas.
Okay, I understand.
That way, okay?
Because
gravity is that way. Because a parabola is, if there is no acceleration horizontally, then axis is down. But here is also acceleration horizontally. Directrix is still horizontal.
Sakalda.
Yes.
All the parabola that the ball will make will have one single directrix.
All the parabolas have the same directrix because recall what was directrix. Directrix was a line at the altitude where potential energy equals to full energy. But there is no energy loss. There is no change in full energy. Because of that, there is no change in directrix. Energy is not lost, so full energy is still the same. Directrix is still the same. Directrix is defined just by the full energy. Kinetic plus potential.
Okay.
Okay, so my recommendation is consider these two lines, this line, and consider the touching point of arbitrary segment of parabola. Consider arbitrary parabola and consider the touching point. And then based on that, try to figure out where is the focus. Find where is the focus. This is my hint.
Doesn't it depend on the velocity, which is parallel to the slope?
What depends on velocity?
The radius of curvature or the focus.
I am asking the position of focus, which you would could deduce based on the directrix. Directrix helps you to find where is focus. Don't need to think about velocity or something, things like that. Just think about directrix, and based on directrix, where is the focus. Also, don't forget geometrical properties of parabola.
I proved that it's a straight line.
How are you?
Hello?
Yes.
I get that it's a straight line and its slope is, wait a minute. Oh, I will find the slope. Is the slope is 1 minus cotan alpha?
No.
Is it 1 over this thing?
No.
Oh, no.
So guys, perhaps I should help you a little bit.
Perhaps.
A little bit.
Okay. So let us now draw here a vertical line through this point. Okay. And now I am asking from this point here, to which distance and at which angle is directed the focus?
Shouldn't the focus be perpendicular to the
Sorry?
peak, to the
Sorry?
tangent of the peak?
Once again?
Shouldn't so oh, this angle here. Okay.
Yeah. So from this production point here, at which direction should we go in order to reach the focus? And to which distance should we go? These are hints for you. And if you answer to these questions, then basically there is only a little bit to do. You're almost there. Then you'll find the answer to the problem.
Mr. Calda,
Yes.
can we solve the problem?
Yes, sure. Did anyone get the answer here? No?
Teacher, are we going to have another problem after this?
Yes, sure.
Because we have only 20 minutes.
I know.
Mr. Calda, I think ending at 9 p.m. is too late. Because, yeah, 9 p.m. is too late. I think anything after like 7:30 or 8, like we kind of get to like really tired.
I think you will get tired either way after 5 hours working. It will not help if we start earlier. Just I quite well understand that, but just please try to bear with it. Because during the intensive training in Coast you had 8 hours, and I know after 8 hours you are really tired. After 5 hours you are still a little bit less tired, but yeah, well, don't make illusions that if we start 1 hour earlier you are less tired at the end.
I'm not meaning because we are tired. I mean, if we do not have another problem, let's solve it in the last 10 minutes. If we do not have another problem.
Okay, I had here 2 helping questions. Let us try to do it slowly together. So I gave you 2 helping questions. First, what is angle here? Now, can anyone of you tell me what is the angle here?
Which one?
Okay,
90 minus alpha.
how to find at which direction this focus is directed? At which direction should we look for the focus?
Shouldn't the line be perpendicular to the surface?
No.
Will the line be perpendicular?
No, not perpendicular. Not perpendicular.
Is the angle 2 alpha?
Which angle is 2 alpha?
Between the 2 rays, the incident and the reflected.
So basically, this what we have is that since this vertical direction is reflected by the parabola to a focus, so this is reflection from this parabola, which means that this angle here equal to that angle here. Okay, do you agree, everyone?
Agree.
Yeah. Agree. On the other hand, this angle here equal to that angle here.
Yes.
So this angle here equal to that angle here.
Yes.
Now, this was the first thing to notice. Second question is, from this point, how far is the focus?
It's the same as the distance from the point to the
yeah, because this is on the point on the parabola, so it is at equal distance from focus and directrix. This is directrix, so this line here equal to that line here. Okay.
Yes. Yes.
And now, can you put everything together? Where is the line? How can I find the position of the focus of this curve here? So here it is. It is here. But now we have one triangle, and let us draw another triangle also now. So what can you tell about these 2 triangles?
They are identical.
They are identical because angles are identical. This is common side, which has the same length, and this side equal to that. So there is like side, angle, side, property. So if these are respectively equal, 2 triangles are equal. If sides, two sides, and angle between them are respectively equal, so two triangles are equal. So this triangle equal to that triangle, which means that this angle here equal to that angle here. Now,
Okay.
now can you see at which line all the foci lie?
At what?
Now can you see at which line all the foci lie? So this is a throwing point.
So from what I can observe, it's always if we just plot 2 points, we can find the slope from there.
It's easier than that. This angle here is alpha. This angle here is also alpha. So we draw from a throwing point angle on the slope to alpha, and we reach a focus. And it was arbitrary parabola. So this is valid for any parabola over there. So all the foci lie on that slope.
Okay, yeah, so the slope would be negative negative sine to alpha.
So all the foci lie on a line which is inclined by 2 alpha.
Yes.
Why is this is that point the peak of the parabola? Like,
sorry?
why is the distance from the directrix equal to the distance of the focal point? Why is this the top of the parabola?
For any point of the parabola, the distance from the directrix equals to the distance of the focus.
Oh, any point.
Yeah, this is the property of very definition of directrix. Directrix is such a line that a distance of a point from directrix equal to the distance from the focus.
Oh, okay.
Okay?
Okay.
Teacher.
Yes. So what did you want to say?
The angle alpha again, please. For how did you figure it is alpha? Okay. No need. I figured it.
Okay.
So another problem.
Yes, another problem. Now, well,
teacher.
Sorry.
So this the lower for the reflected light, for the incident light, the angle between the tangent and the incident light will be 90 minus alpha. Am I right?
If we take a vertical line, it is reflected to the focus. So yeah, this angle here is this is slope angle alpha. This is 90 minus alpha. Yes. If that's what we ask. And then yeah, this is reflected so that the angle 90 minus alpha here equal to the angle 90 minus alpha over here.
Okay.
Because here we choose a point which is tangent to this line, which is also anti-alpha. So at this point, the parabola has the same tangent. So it is reflected because of that on the that 90 minus alpha.
Clear.
Mm-hmm. Now, next problem.
Yes, next problem.
Okay, guys, actually, now, what is the situation? We have done with you quite a lot problems on kinematics. Maybe we should finish with kinematics and start tomorrow doing other topics. What is your feeling?
What are the other topics going to be?
Mechanics, celestial mechanics, dynamics, statics.
Yes, I think it's a good idea.
Yeah, we're gonna. If we have at the end, we have more time. We can still do some kinematics problems, but that would be the plan. But now it would be very nice of you if you could try now solve. Maybe tomorrow you have before lecture you have some time or something like that. There are still some nice problems on mechanics, on kinematics. First, of course, you can open the kinematics booklet. Now, with all we have done with you, you should be able to solve any problem from there, basically. And there are a lot of nice problems for exercise. Now, other than that, there is one problem which I really recommend trying. This is the first UFO problem about the water hose. Or was it second UFO problem? Second UFO, yeah. Second UFO in Latvia. When you had a water hose, so a stream of water comes from the origin, and then you change the direction of the hose so that the water draws something like a certain shape, something like, now how it goes, something like something shape, something like that, maybe. Maybe. This is a photo taken of the stream of water.
Which year for UFO?
UFO in Latvia. Second UFO in Latvia. Problem number 3. Okay, just open the problem and try to solve it. It is a very nice problem, and once you have done it, we can later discuss together the solution over there as well. Now, we are not going to do it right now. Read the problem and try to do it. We have just 8 minutes left. Let us do a simple problem. It's like revision what we did before. So you have a bike, and then the bike has wheels, it's spokes. Spokes of the wheel. Okay. And now this wheel is rolling on horizontal surface. And now you take a photo of this. But the exposure time is so long that because of motion blur makes most of things smudged, so there is no clear picture. But certain parts, certain pieces, certain small segments of the spokes are still clear. They are sharp. So where are the spokes sharp on picture? Is this clear, the problem? Wheel rolls, we take a photo but long exposure time, so everything is blurred, except for certain small pieces of spokes.
Can I answer?
Sorry?
I think I know.
Yeah, and so where?
Wait.
On the right and left edges, because
no, not on right and left edge. No.
I didn't understand what's going on.
Sorry?
I didn't understand what's going on.
Okay. If you take a picture with long exposure time of something which is moving, then the picture becomes blurred because like different positions are overexposed on each other. If object is at rest, picture is sharp. If it's moving, it is smudged. here is what is happening. But if you take photo here, some pieces of the spokes are sharp. Some certain points on the spokes are sharp.
Point.
The rest is much. The rest is blurred.
The bottom point.
Yeah, bottom point is clearly sharp because this doesn't move. That's right. What else? Bottom point is touching the surface, and this is clearly addressed, so this is sharp.
حسن ترجم السؤال بعد إذنك.
Sorry?
Okay, so he wants me to translate, but I have a question.
Yes, please.
So you want this wheel?
Yes.
Has spikes going from the center to the side, so it's like a bicycle wheel.
Yes.
Okay. صادق wants me to translate. So الحين صادق تخيل ان عندك كذا يعني كفر ولا شيء قاعد يدور كأنه كفر مو دباب سيكل.
طيب.
ويسألك ويقول لك انه قاعد يتحرك يعني بسرعة وانت صورته بكاميرا، والكاميرا لان الاكسبوجر تايم حقها، لان الكاميرا وش تسوي لما تصور يعني من الضوء، ما اعرف كيف اشرح، بس يعني ان لو حاجه تتحرك بسرعه تصير مشوشه كذا، ويسالك وين النقاط اللي تكون حاده يعني ما هي مشوشه.
ايوه خلاص.
Calder.
Yes.
There are no rest points other than the bottom point.
There is a whole set, a lot of points actually. Those points lie on a certain curve. Okay, let us see. As a point on a spike is not blurred if the spike moves along itself. So let us say if we have here a spike, and if this region here it is moving parallel to itself, it is not blurred. If it moves perpendicularly, it becomes blurred. But if it's parallel, it is not blurred. Okay? So we need to find those points on the spikes that the motion is parallel to the spike. Okay?
What if it's neither parallel nor perpendicular?
Yeah, velocity needs to be parallel, because if it has certain component which is perpendicular, then it makes it blurred.
So this is for a point on one of the lines.
Yeah. So if we take, if we find a point which moves parallel to itself, to the spike, then this is not blurred. This is sharp.
But aren't they all moving perpendicularly? Oh, no. Okay. I see.
So now, any of you, do you have idea how to approach this? Well, we have learned, studied with you many ideas on how to deal with kinematics problems. Which one we are going to use here?
The frame.
Yes,
Sorry?
I have an idea.
Yes, please.
Since the lowest point at rest, it must be the instantaneous axis of rotation.
Very good. Yeah, it is instantaneous center of rotation. Very good. Yeah, so we are going to use instantaneous center of rotation. So this here is instantaneous center of rotation, and any point has velocity vector which is perpendicular to the radius vector drawn from the touching point. So now we want to have, if we take a spike, we want this here to be right angle. If this is right angle, then this is perpendicular. If this is also perpendicular, then this is parallel to that. So we want this angle here to be right angle. Angle between the spike and the radius vector drawn from the touching point. We want this to be right angle.
I think then if this is the case, then there will be a point on the lower left corner of the. I can't show you directly. I can't
we
point
want
to
to have like that. Okay, this point here now because here is right angle, it moves along here. This is sharp. So where are the possibility? All the points which are sharp.
A circle.
Yes, this is circle. We have Thales theorem that if we draw a circle like that, then these points are here. We have everywhere here right angle. Okay. So all the sharp points lie on this circle here. All right.
Mr. Khalid, what is the radius of this circle?
What is
the radius of
radius?
this circle?
Radius is half of the so Thales theorem states that if we have diameter of a circle and then you take arbitrary point on the circle, then this is here right angle. This is Thales theorem. That a circle of a right triangle hypotenuse is the diameter of the circle. This is like a particular case of the theorem about inscribed angles, which states that if you have inscribed angle here, this is 2 times smaller than the central angle here. Here is alpha, here is beta. Alpha equals beta divided by 2. Here the central angle is 180, and 180 divided by 2 is 90. So based on the inscribed angle theorem, we see that all the points which are on this circle, which is drawn on this spike here as a diameter. We take this vertical spike here as a diameter, draw a circle, and all points on the circle are sharp.
Okay.
All right. Everyone happy?
Happy.
Teacher, when you taught the instantaneous the lowest.
Sorry?
Why both the angles are going to be 90?
Okay. Once again.
Why both angles are going to be 90 degree? One because it is instantaneous, and the other because it's going to be one of the radiuses. Is that the reason?
Okay. If we draw, when I spoke about the instantaneous center of rotation, so we knew that if we know the instantaneous center of rotation, we know all the velocity vectors, because velocity vector of arbitrary point can be found as a vector which is perpendicular to the radius vector, and it is equal to omega times r by modulus r is distance. So velocity vector, if we know instantaneous center of rotation, velocity vector is perpendicular to the radius vector. This is what we are using. So we want the velocity vector to be parallel to the spike. So our radius vector must be, because of that, must be perpendicular to the spike. So we want this angle here to be right angle.
Okay. I got it.
Okay. All clear now to everyone?
Yes.
Okay, so now we more or less finished. Of course, we could have done more problems. We have a lot more problems on the kinematics, but we need to stop somewhere, and that's what we're going to now. But tomorrow, when we start, we go point by point all the main thing which we learned here. So that try to memorize, try to be able to use these things next time. So first they make a brief revision of everything what we had here before during the first 2 days, and then we go to statics. Okay.
Okay.
That is okay.
Okay.
When will you upload the
yeah, this is uploaded now. Let me give you the link. Let me give you the link.
أي سنة حدة اليوفو اللي حط هذا الستار؟
Sorry.
2019 ارسلتها بالجروب.
So here is the link to the playlist. I am going to add to that playlist. So next time I don't need to send you the link because it's there. Now, I also give you here now the link of CFA problems. Yes, so here are the problems. Here, problem number 3. All right. And tomorrow we speak. Please, really, I recommend maybe what you can also do. Please try to have a look on this problem number 3 of UFO. So tomorrow morning, maybe we should discuss the solution of this problem number 3, and there is one more small thing what I can say about this problem, if you think it's okay.
Of course, it's okay.
Yeah. Okay. So tomorrow morning we still the last thing about kinematics is we have a look on this UFO problem. But we are not. I am not going to let you solve it tomorrow. So I hope you can try solving it like your homework before tomorrow morning. Before tomorrow we start 4 o'clock. Please have a look and try solve it. So I expect all of you already have tried to solve it, and then we look together.
Okay, we will.
All right.
All right.
Then good luck everyone, and see you tomorrow.
Thank you very much.
You're welcome.
See you tomorrow.
See you tomorrow.
Have a good night.
Yeah.